Hey everybody, and welcome back to Calc 3 Online. So the plan for today is to talk about some cases that show up with double integrals involving regions that are neither type 1 or type 2. So you can definitely get that. And just to kind of show you that, I thought I'd start with this. So we have a lot of regions which are actually both type 1 and type 2. Probably the easiest ones are just things like some sort of, square, rectangle or something. This is something that is really easy to do an integral or double integral with. You can do it as a type 1 or a type 2. But if you imagine a circle, if that was actually a circle is something that's neither type 1 or type 2, right? So you can't just, this is, some sort of implicitly defined function, and you could split it up into like a plus and minus square root thing and kind of do it that way. But there's actually going to be a better way when these things are neither type 1 or type 2. And that's actually what we're going to get into today, and that is polar coordinates. So a lot of the times, if the region you're trying to integrate over is some sort of like circular or curvy thing, like a circle or an ellipse or something like that, it's an indication that maybe you should use polar coordinates. And we're also going to learn about, we do triple integrals. There's some other coordinate systems. There's something called spherical coordinates, and you're going to learn about that. And so if something is like spherical, like in 3D, and that's what you're integrating over, then you should use spherical coordinates. And so the region that you kind of integrate over is an indicator for what coordinate system basically to use. And so the trickiest thing when you change coordinate systems is to know what the area element that you're, like the dA. We're also going to eventually integrate over 3D things, so we're going to have like a dV instead of a dA. But when we do these problems, probably the trickiest part is knowing if we switch coordinate systems, what that change does to this part right here. And for polar, it still truly comes from like area of a rectangle. So our dA is, like an infinitesimally small sort of, polar rectangle, we'll kind of call it. Basically, the idea is like, if you imagine this continuing like this over like maybe a circle or something, you're basically splitting the circle up into little before we did it where we took a rectangle and we just split the rectangle up into little quadrants. And now we're just doing it for polar, but our little pieces are in our grid kind of have this structure. And to find the area of it before, we just literally did length times width, and we got the delta x from that, or the dx dy, right? So maybe I should draw what I'm saying here. So if we had, like a grid like this that we're integrating over, this little chunk in here, this part is like a dx, right? And this part is a dy, which is why we, our dA in rectangular, was just dx dy, or dy dx. So we still are doing that, and it's still just literally like area equals length times width. But the way we find the length and width are a little different. So the, you can call this the length or width. It doesn't really matter. But part of it is really just, the change in the radius for my polar. So part of, let's just call it, let's call this length, okay? So dr is going to be part of my area element, okay? And then the other dimension, let's do the width. It's this part right here, and that is actually an arc, right? Like if you think about it, right, it's like some circular thing that keeps going around. And so this arc right there, but this is really an arc, and so we need to do arc length to figure that thing out. And if you remember, with arc length and polar, it's really just, we usually use L. And so it's just R times theta. And so theta is the angle that arc spans right there. And that span is just the d theta, the change in theta. So this part right here would just be rd theta, right? And so what this means is that my dA for polar, if I switch to polar, I'm just going to have to, for dA, I put in r dr d theta, okay? And it's kind of weird, but you can see it down here. dA is switching to r dr d theta, and it really just comes out of the area of a rectangle still, but it's like a polar rectangle, so you have to do that extra little part with arc length. And then the other thing you just got to remember to be careful about is when you convert, right, from rectangular to polar, don't forget that x is r cos theta and y is r sine theta. So if we do conversion from, our problem into polar to help us, if the region is something like a circle or whatever that we're integrating over, then you have to make those three conversions. X, Y, anytime you see them, you swap that in, and then dA is actually r dr d theta. All right, so for this part right here, I just want to take a really quick little bit of time to just review some stuff that you should know about polar. There's a lot to talk about with polar, and from pre-calc, I'm not going to ask that you can do everything with polar that you've seen before, but there are some basic things that I just want to make sure you know. For example, I don't really plan to do many problems with the rose curves, these things. And honestly, even the spirals, and the spiral actually kind of makes sense because this is a pretty straightforward equation, because it's just saying the radius is changing proportional to that angle, right? So with smaller angles, it has a smaller radius, right? So at an angle of 0, it's got a radius of 0. But as you go around, right, the angle is getting bigger, so its radius gets bigger, and so you get a curve that goes a spiral, right, out, out, and out. So that one maybe I feel is fair, but probably the ones that you definitely just want to make sure you know are up here. And also this one, a circle. So a circle is actually probably the easiest one, so it's a little hard to see, but the units here are 1, 2, 3, and a circle is truly just, in polar, r equals, this one would be 3, because it's just the thing that it's a constant polar graph where the angle can be anything, right? You can go through the full 2 pi or keep going around and around and around, but the radius is just fixed to be 3. So you should know that one. And then these other ones, okay, the way that I kind of remember these, so we know that x equals r cos theta and y equals r sine theta in polar. And so, the ones where you have a circle, if the circle is on the kind of on the left or right of the y-axis, that's left or right is an x, and that's your clue that it's the cosine one. And this one, the radius is just 1. So let's do blue or something. So this equation would be r equals just 1 cosine theta. If this circle went out to 2 or something like that, then it's just 2 cosine theta. If this circle was on the other side, right, the negative side of the y-axis, then it's negative cosine theta. Kind of similarly here, when you see the circles like above or below the x-axis, left, like above or below is like a vertical y direction, and so you would get r equals, in this case, just sine theta. And again, like if it went out to 2, then you would have 2 sine theta, but we don't have that. So those versions of like the sine, basically these ones, the a sine theta, a cos theta for different a's, those are good ones to know. And then cardioids are really good to know. So this one, the way you want to think about it here is if you've got the heart is sort of, so cardioid, they name this because it kind of looks like a heart, right? And if it's a heart left or right like this, then it's a cosine one. And just like before, this was on the positive side, so it's cos theta, but we want to be on the left side now, so it's a negative cos theta. In this one, we would just have r equal 1 minus then cos theta. So, these ones, you should just go, like, you can go to Desmos if you don't remember, and, like, plug in different A's and B's and just kind of see the pattern that you get. Really, these are the same kind of thing. And those are the ones that, like, are good to know. You can also like add sliders for A's and B's, and you can see how you can go from like a circle and then to cardioids to the limicon, this thing. I think that's how you say it. But those are the ones that kind of show up the most in polar and are good to know. All right. So I want to just go through an example now. So I want to evaluate this thing over the region in the upper half plane bounded by the circles x squared plus y squared equals 1 and x squared plus y squared equals 4. So like all double integrals, it's always good to just start by graphing things. So let's do, let's say 1, 2. So x squared plus y squared equals 1, right? Let's do 1, 2, 1, 2. Would look like, because it's in the upper half part of the plane up here, we don't need to draw the bottom part of the circle down here. So we have just that part for this, right, that we need. And then x squared plus y squared equals 4. We got that. Pretty good arc I just drew. And so the region that I'm integrating over is this part right here. And, since it's a curvy region, that's kind of my clue that it could be a good problem for polar. And so I want to set up bounds and switch to a polar integral, polar double integral to do that one. So if I go and set this thing up, x is r cos, right? So we would have like 3 times r cos theta, because it's 3 times x, right? And then plus 4y is r sine, so r sine theta squared. And then dA, right? When we switch it, based on this thing, it's going to become an r dr d theta. And so this part right in here is just my r dr d theta. And in terms of bounds, right, dr is the radius, and the radius you can see goes from 1 to 2. And so this bound is 1 to 2. And then d theta is the angle, right? And so we start here, and we're going through half a circle, which is pi radians, right? So for d theta, I do 0 to pi. And that's the setup. and then you just got to go and simplify and plug and chug and all that good stuff. So you truly do need to, this, R is basically being distributed here to these two terms. And, this dA basically applies to this whole thing. So it really is like this is one expression and then this is another expression and we're multiplying them. And so that R does get multiplied in there. All right, so if I go set this thing up, or go simplify this, we would have 3r squared cos theta. And then you got to double distribute, all that good stuff. You're going to get, when you multiply in the r here too, you're going to have r squared times another r, so r cubed. And then you'll have, or not double distribute, it's like you just put the 2 on both these, right? And then you'll have sine theta. And then you have a dr and a d theta. And then dr is a nice integral because you literally it's like a polynomial integral. So you'll have like r cubed over 3, and then that'll cancel there. And then r to the 4th over 4, and so the 4's cancel there. So this whole thing just becomes r cubed cos theta plus r to the 4th sine squared theta, evaluated from 1 to 2 d theta. And then if you just go and plug in 1, 2, you should see that you get 7 cos theta plus 15 sine squared theta d theta. And both of those integrals are nice. So this one, is very straightforward. And then sine squared's a nice one too if you just do the half angle identities. So I think I'm going to have to erase it here. But sine squared theta is just 1 minus cosine 2 theta over 2. I can show you if you want where that comes from, but that's a good identity to know. That's just the half angle formula. And there's one for cosine squared also. And that's basically a much nicer integral to take, right? Because if you split this up, cosine 2 theta, much nicer integral to take because you can just do the trick where you integrate cosine and then just divide by the 2. And so that's how I would do, I would convert sine squared to that, then I would integrate this, which is much easier than integrating this. So it's a common kind of trick with those. Basically, you have the 7 cos theta, and then you would have a 15 over 2 from that trig identity, the half angle, and then a 15 over 2 cosine 2 theta, d theta. And then now I would integrate. And if you go and integrate all that, you're going to get 7 sine theta plus 15 theta over 2. And then minus 15 over 4, because you're dividing by the 2 from in there. 15 over 4 is sine 2 theta. And then if you evaluate that 0 to pi, you should just get 15 pi over 2. Okay. But yeah, this is a good example of one that is definitely much easier with a switch to polar. So anytime you see something with these kind of curvy regions, like something circular, that's probably a clue that polar is going to help you. All right, so this is a good example that uses kind of a lot of tricks related to polar and honestly just like algebra in general and things like that. So let's first kind of get our hands around the idea of what even is going on. So it says we're going to find the volume of a solid that lies under this paraboloid, okay, and above the xy plane and inside this cylinder, okay? And so basically the fact that we're underneath the paraboloid and above the xy plane means that this is the thing that's going to go in my integral, right? So I'm going to basically do a double integral of x squared plus y squared d8. That's the problem. We know we're going to be above the xy plane, which is nice, and we're inside this cylinder, and this is something that we should probably understand what that kind of looks like and where that cylinder is. So that's where completing the square could be helpful. So if you just do, if you write this as x squared minus 2x plus y squared equals 0, and you complete the square, all right, you're going to have x squared minus 2x plus 1 plus y squared equals 1, right? And then this these x terms basically factor into x minus 1 quantity squared. And if you think about what that looks like, right, it's just a circle with a center at 1, 0, and then it's got a radius of 1, right? Oops, so that's a 2. And then it's a 1, negative 1. So it's just a circle that goes through those points. And this is where some knowledge of polar graphs is going to be important, because it's very much like this one right here, except instead of a radius of 1, it's got a radius of 2. So this graph in polar is r equals 2 cos theta. Right? And you can honestly see it too if you just go and plug in x equals r cos and y equals r sine theta, and you just simplify it, you'll get this. There are some polar graphs you just want to kind of know for sake of time, and instead of having to go and convert and see, oh, I get that, it's good to just be able to jump there and just know it. All right, so what we basically are doing is we're integrating over this region, right? Because this is in the xy plane, and underneath that surface. And so since it's curvy, we should probably convert this to polar. So I'm going to go and start plugging things in here. So in polar, and x squared, x is r cos, so we're going to have r squared cos squared theta, and then y is r sine, so we're going to have r squared sine squared theta, and then that's this x squared plus y squared, and then dA is r dr d theta. And my bounds, right, we know we go from so in terms of r, right, we can see that the smallest r, because it truly does go through the origin, would be 0, and then we just go out in r to that surface, or that 2 cos theta, right? So the first bound's 0 up to 2 cos theta in terms of r, and then the angle is, this is maybe a little bit, weird to kind of see it this way, but you can think of the angle as going from negative pi over 2, right? Like over here, up to pi over 2. And so if you do it that way, you can also, if you don't... So the weird reason the angle's a little weird is because I think it doesn't quite look like you're getting the negative pi over 2, but you really do here. And then you map out through the full thing, right? And you still end up back there. So it's a little hard to see. You might want to plug in some numbers, some of those angle values there. And you could see that you really do map out that full circle in basically these pi radians between negative pi over 2 and pi over 2. So that is the setup. And then simplifying it isn't so bad, because if you factor out an r squared in here, you'd get a cosine squared and a sine squared, which is 1, right? So really, you factor on r squared, you get a 1, and then you multiply by an r. And so this problem really becomes r cubed. That's literally the whole integral. 0 to 2 cos theta, negative pi over 2 to pi over 2. And then the first integral is really nice. You get r to the fourth over 4, ranging from 0 to 2 cos theta, d theta. And then so let's see what it is. So then plugging this in, the zeros can be really nice. 2 to the fourth, 16. 16 over 4 is 4. So what we really get there is negative pi over 2 to pi over 2. We're going to get a 4, right? Because 16 over 4 is 4. And then we would get cosine to the fourth theta, d theta. And that really is the same thing as cosine squared theta squared d theta. And cosine squared, I would also just use the way we did over here. To simplify sine squared, we used a half angle identity. I would just use the half angle identity for cosine squared now. So if you go and plug that thing in, you would get this. And, I just dropped it too. So notice I also switched the 4 to an 8. So I did the kind of thing where, this was a symmetric region above and below the x-axis, right? So if I just double my integral of half that, right, I should get the same amount of area or volume, sorry. So I'm just doing, I'm saying that this region is going to give me the same as this region, so I can just double it. So 4 went to 8. Then I don't have to deal with this annoying negative pi over 2. And then this is 1 plus cosine 2 theta, although that line should keep going, over 2, and then squared. And then you basically now have to go and double distribute everything out there, which is kind of annoying. But if you do that, you would get this. And this 2 is popping up because 2 squared is 4, 8 divided by 4 is 2. So now you get this whole big messy thing. And what I did in here, right, was I had a cosine squared 2 theta, and then I just used half angle identity again, basically. So it's a half angle inside of a half angle. And that that's going to be really kind of a common trick you'll see in a lot of these problems, is just anytime you see squared sines or cosines, which you do get a lot, just use half angle identities. So that's how I got cosine of the 4 theta. So actually I'm going to need to get rid of all this. And then if you finally have it in a form where all these integrals are really nice, you can do the kind of thing you just divide by 2, divide by 4. And so you can just go and plug and chug that integral. You get 3 pi over 2 for this thing. That's it. But this one is a good example of probably about as hard as you could kind of get with polar right now. It uses a lot of good tricks with completing the squared to figure out the region, knowing what that region is in polar. You got to go set it all up, and then you use you'll use the same trig identity, but use it twice, and you got a lot of bookkeeping to keep track of, doing the kind of doubling thing that you see in Calc 1. So it's a good problem to make sure that you understand.